Okay, I'm back, and now let's talk about some of the surface features that you would find on the planet Mars. The first one is dust storms. That it has these huge dust storms that cover the entire planet for months on end. And it has dust storm seasons, so it would have these major dust storms occur in the spring and then they occur in the fall. And so one of the reasons for these dust storms has to do with the temperature changes that occur when it goes from summer to fall to winter to spring again. So if we were to draw a picture of Mars, it does actually have water. It has water up here at the North Pole, and then it's got water here at the South Pole. So let's say that it is winter time. So during the winter time, carbon dioxide in the northern hemisphere will settle on the North Pole so that you get frozen carbon dioxide, or dry ice, appears at the North Pole. Okay, now let's say it's starting to warm up in the springtime so that this frozen carbon dioxide starts to turn back into a gas, and then it's got to go somewhere. So it wants to go somewhere where it's cold, so it migrates down here to the southern hemisphere where it starts to accumulate down here. And so this transfer of carbon dioxide in the spring and in the fall is one of the things that helps to trigger these Martian dust storms. It has a rusted surface. So they call it the red planet because it's actually the color red at the surface. And this is rust. So if you recall, basalt, which was an igneous rock, has lots of iron in it. And then that iron mixes with oxygen to make rust. Okay, and so you're saying, well, where did that oxygen come from? Okay, so this dates back to early in its history when it had oceans. Their oxygen was able to mix with the water, and then that water then rusted rocks, and so it made these things that are called red beds. And so at the end of the video series, we're going to talk about the geological history of the Earth. And when we do that, we're going to talk about the red beds that were formed here in the United States. And today we mine lots of iron from those. And of course, you're also saying, but where'd the oxygen come from? So water is H2O. So when water gets into the atmosphere, it can be broken apart by lightning or by ultraviolet light into hydrogen and oxygen. And then the hydrogen escapes, and then the oxygen can combine with the rocks to make rust. Another thing about Mars is it has these dry river channels. So that's an indication that at one time it had flowing liquid water on the surface in order to be able to do this. Now there's two lines of evidence as to where did these river channels come from. So one is that the river channels are billions of years old. And so this represents when Mars was very young. It had an ocean. It had a dense atmosphere. It was kind of Earth-like for a short period of time. And so it would have had rain, and it would have had rivers, and it would have had these rivers channels. The other line of evidence is that they think it could be due to flash floods, that there might be some pockets of water ice under the ground, and then when they get heated up by being next to an underground hotspot or magma chamber, then that water changes to steam, and then it blasts its way out of the ground. And then for short periods of time, you have these horrendous floods on the surface of Mars, but the water very, very quickly evaporates because there's not enough pressure. Remember, we said if you reduce the pressure, then that will cause water to boil more easily. So that what you're left with is just these dry river channels. Another thing interesting about Mars is it got hit by an object about the size of the planet Pluto early in its formation. And it got hit up here in the northern hemisphere, and then it made that colossal crater there called the Borealis Basin. So that's a picture looking down onto the North Pole of Mars, and you can see the size of that crater as a result of that. So it occurred very, very early in the formation of Mars, the same way that Earth got hit very, very early in its formation, and then the debris formed the moon. Another thing is the Valles Marianus. Okay, so that's a crack that runs across Mars. So if we, you can see the crack in that picture up there, but it's better illustrated if you go to that little computer program down below and then look for the Valles Marianus. So it's a crack that is about the size of the United States, and it is about twice as deep as the Grand Canyon in the United States. So when they first saw this thing, they thought, well, it's a river. So a river carved this gigantic canyon. Well, it didn't. So what we think that the Valles Marianus is, well, you tell me, what kind of a plate action would make a crack? Okay, that's where the plates were being pulled apart. That was a divergent zone. And so what we think is that that is a place where the plates were beginning to pull apart, but the planet cooled off so quickly that the plate tectonics shut down. And so all that you're left with is this colossal crack. And then you got Olympus Mons. So Olympus Mons is a volcano that is at least 2 times taller than Mount Everest. So we don't have volcanoes like that on Earth, that big. So that volcano is very similar to the kinds of volcanoes you'd have in the Hawaiian Islands, where you got very runny lava comes up and then it spreads out and makes a flat shield volcano. But they never get that big in Hawaii, because what is Hawaii doing? So Hawaii, the plate is moving off the hot spot. So then what happens is, instead of getting one gigantic volcano, you get a whole bunch of little volcanoes as the plate moves. So on Mars, the plate is over the top of a hot spot, but material just keeps coming up and making the volcano bigger and bigger, and the plate isn't moving anymore. So that's what we think that Olympus Mons is. It is a very big volcano, but it's actually not the biggest volcano in the solar system. So we'll find out later what that is. I say the word later quite a bit, don't I? Sorry about that. Okay, so here's our summary of the terrestrial planets. So if we start off with the moon, the atmosphere is very thin. Because of that, the pressure is very low. The temperature has extremes in hot and cold because the atmosphere is so thin. It is geologically dead. It has the lunar highlands and then the maria. No magnetic field, no oceans. And then the reason why it evolved the way it did was it was very small. If you look at Mercury, atmosphere is very thin, composed of hydrogen and helium, very low pressures because the atmosphere is thin, large temperature swings because the atmosphere is thin, and also because it's very close to the sun. The geology, dead. has a large iron core, does have a small permanent magnetic field like a bar magnet. No oceans, and then again, why did it evolve the way it did? Very small, too close to the sun. Okay, now let's take a look at Venus. It has the very thick atmosphere composed of carbon dioxide, very high pressures because it does have the thick atmosphere, very hot because it does have the thick atmosphere, the greenhouse effect. It does have hot spots, but no plate tectonics, very thick lithosphere, no magnetic field to speak of, and then no oceans. And why did it end up the way it did? Too close to the sun. Okay, we'll talk about that in just a moment. Then Earth. So Earth is the Goldilocks planet. So we've got an atmosphere that's not too thick, it's not too thin, temperatures are just right, we've got plate tectonics, we've got a nice magnetic field. And then Mars, okay, a very thin atmosphere composed of carbon dioxide. It has those terrific dust storms. Because it has the thin atmosphere, it has very little pressure. It's very cold because it's very far away from the sun. And it doesn't have a thick atmosphere to cause the greenhouse effect. It has hot spots, Olympus Mons, Valles Marianus, river channels, dry river channels, no oceans, and then what went wrong? It was too small and too far away from the sun. Okay, in our next segment, we're now going to go through the geological history of the solar system.